Imagine that you open the refrigerator, and instead of yogurt, there is a miniature black hole. Absurd? In space, such things happen all the time, only instead of a refrigerator, there is an endless emptiness, and instead of yogurt, there are entire galaxies that behave as if someone rewrote the laws of physics after the fifth drink. Let's figure out what oddities lurk in the darkness between the stars, and why scientists still scratch their heads when looking through telescopes. Let's start with the most obvious question: what is considered an anomaly in general? In short, everything that makes physicists nervously smoke in the corridor. The cosmos is full of objects and phenomena that don't fit into our cozy theories. It's as if you have been assembling a puzzle with cats all your life, and the last piece turned out to be a piece of a submarine. Take black holes. It would seem that everything is clear. Gravity is so strong that even light cannot escape, but there is a nuance. At the center of a black hole, according to calculations, there is a singularity, a point of infinite density, endless. Our math models just break down at this point, like an old calculator when you try to divide by zero. Physicists call it a problem, but it's really just a confession: guys, we have no idea what's going on there. And black holes sometimes eject jets, the most powerful streams of matter and energy that fly out at a speed close to the speed of light. Imagine a vacuum cleaner that, instead of sucking in, suddenly begins to spew a stream of dust over half a galaxy. These jets are so bright that they can be seen billions of light years away. Paradox: the darkest object in the universe creates the brightest fireworks. But black holes are just the beginning. There are worse objects, neutron stars, for example. This is what remains after the explosion of a massive star. Imagine that you took the sun and compressed it to the size of a small city. A teaspoon of neutron star matter weighs about 1 billion tons. If you've ever been told that you're a heavy person, just remember neutron stars and you'll feel better. Some neutron stars are spinning very quickly. Pulsars are neutron stars that rotate at speeds of up to 700 revolutions per second. 700. This is faster than a light bulb flashing in the stairwell when it's time to change it, and at the same time, they emit radio waves like cosmic beacons. The first such thing was discovered in 1967, and astronomers even thought that it was a signal from aliens. They called him LGM-1, Little Green Men, Little Green Men. Then, of course, it turned out that it was just nature showing class. But the first few weeks were hot. And now let's talk about what we do not see, but we know that it exists: dark matter. It's like that guy at a party that no one has ever seen, but everyone knows he's out there because somebody ate the whole salad. Dark matter makes up about 27% of all mass and energy in the universe, but it does not emit light, does not absorb it, and does not interact with ordinary matter at all, except for gravity. How do we know that it exists? Because of the way galaxies behave, they spin faster than they should, based on visible matter. If galaxies had only the matter we see, they would scatter like fireworks, but they stick together. It means that there is something else there, something invisible, which glues the whole structure together with its gravity. Physicists have been searching for dark matter particles for nearly a century. They build detectors deep underground, where nothing interferes. They expect that at least one particle of dark matter will collide with ordinary matter. For now, there is silence. It's like trying to catch a ghost with a butterfly net. But if dark matter is a mystery, then dark energy is a mockery. It makes up 68% of the universe and causes it to expand faster and faster. You read that right. The universe is not just expanding, it is expanding at an accelerating rate. It's as if you threw the ball up, and instead of slowing down and falling, it began to fly faster and faster. When this discovery was made in 1998, half of the physicists thought that their colleagues had made a mistake in their calculations. They checked it several times. No, everything is correct. For this, they even gave me the Nobel Prize. What is dark energy? Nobody knows. It's as if someone has taken the universe and is constantly inflating it like a balloon, but no one sees the pump. There is a hypothesis that this is a property of space itself, that the vacuum has energy. It sounds crazy, but quantum mechanics does not allow this. However, when physicists tried to calculate how much energy there should be in a vacuum according to their theories, they came up with a number that differs from observations by a factor of 10 to the 120th power. This is the most inaccurate prediction in the history of science. Imagine that you ordered a coffee for $3, and you received a bill the size of the budget of the Galactic Empire. Now about the Great Attractor. It's a gravitational anomaly somewhere behind our galaxy that pulls in the Milky Way and thousands of other galaxies at about 600 kilometers per second. The problem is that we can't see what it is because it's in the avoidance zone, a region of the sky obscured by the plane of our galaxy. It's as if someone very big and heavy is standing behind a curtain and beckoning you to him, but you can't see what's there. According to the latest data, the Great Attractor may be part of an even more massive structure, the Laniakea supercluster, which includes about 100,000 galaxies. We live in a cosmic region that is slowly sliding toward some kind of gravitational center, and we still don't really know what exactly. By the way, about the oddities in scale, cosmic web, if you look at the distribution of galaxies in the universe on a large scale, you can see a structure similar to a spider web or a sponge. Galaxies gather in filaments, between which there are huge voids. These voids, can be hundreds of millions of light-years across, and there's almost nothing there, emptiness. Imagine that you are flying for millions of years at the speed of light and there is nothing around you, not a single star. Not a single galaxy, just darkness and loneliness. One of these voids is the Boötes void. It was discovered in 1981, and astronomers at first thought it was an error in the data, a sphere with a diameter of about 330 million light-years, inside which there are almost no galaxies. Usually, there should be about 2,000 galaxies in this volume. 60 were found there. Where did the others go? Nobody knows. Now let's talk about fast radio bursts. These are short, powerful pulses of radio waves that last milliseconds, but release as much energy as the sun emits in an entire day. They were discovered by accident in 2007, when old data was being analyzed. Since then, hundreds of such bursts have already been found, but for a long time no one could understand where they came from. There were many versions, from neutron star collisions to evaporating black holes and even alien transmitters. Now most scientists are inclined to believe that these are magnetars, a special type of neutron stars with an incredibly strong magnetic field, but some spikes are repeated, and some are not. Some come from the same point, others from different ones. The mystery is not fully solved. Another oddity is Tabby's star, or KIC 846-2852, in 2015, astronomers noticed that its brightness periodically decreases, and in a very strange way, not like ordinary stars with planets, where eclipses are regular and predictable. The brightness of Tabby's star fell by 22%. This is a huge drop. A planet cannot give such an effect. Even a gas giant covers a maximum of a percentage of light. What can cover the fifth part of the star? One idea that has stirred up the public is the Dyson sphere, a megastructure built by an advanced civilization around its star to harvest energy. The internet, of course, exploded, but a more plausible version is a cloud of dust and debris, possibly from a destroyed comet or planet. Observations continue, but so far no aliens have been found. What a pity. By the way, about strange stars, there are stars that should not exist according to our models. For example, Przybylski's star. this is a star with a huge amount of heavy elements in the atmosphere. Europium, holmium, uranium, thousands of times more than it should be. No one knows how they ended up there. Maybe this is the result of nuclear reactions on the surface, or maybe it swallowed some planet, or maybe we just don't understand something about the evolution of stars. Or the star of Prystarok, a variable star whose brightness changes as if chaos is going on inside it. Periods of change are not regular, the amplitude jumps. Models of stellar evolution cannot really explain this. It's as if she doesn't know what she wants to do. Now let's move on to exotic objects, quasars. These are the brightest objects in the universe. A single quasar can shine brighter than an entire galaxy of hundreds of billions of stars. What is this? A supermassive black hole at the center of a galaxy that is actively devouring matter. Matter, falling into a black hole, heats up to millions of degrees and glows so brightly that it is visible from billions of light-years away. The most distant quasars are more than 13 billion light-years away. This means that we see them as they were a few 100 million years after the Big Bang. At that time, the universe was very young, and here is the question: how did black holes with a mass of billions of solar masses form in such a short time? With conventional models, this is impossible. There is not enough time. This means that either the models are incorrect, or black holes were formed in some other way, or some kind of accelerated mode worked there. And then there are the blazars. These are quasars that are pointed directly at us, like a spotlight in the face. Their jets are hitting in our direction, and we see colossal energy emissions. One of these blazars, 3C 454.3, is sometimes the brightest source of gamma rays in the sky. It is located at a distance of 7.5 billion light-years. But it shines so that our satellites detect it without any problems. Let's talk about magnetars in more detail. These are neutron stars with a magnetic field a trillion times stronger than Earth's, so strong that it can distort atoms, turning them into cigar-shaped things. If the magnetar were to be within the moon's distance from Earth, it would erase all information from every credit card, hard drive, and magnetic stripe on the planet, and you would also be torn to atoms. But these are details. Magnetars sometimes produce flashes. In 2004, the magnetar SGR 1806-20 produced a flare that released more energy in a fraction of a second than the Sun radiates in 150,000 years. This is at a distance of 50,000 light-years from us. The radiation reached the Earth and temporarily ionized the upper atmosphere. If such a flare occurred 10 light-years away, it could destroy the ozone layer and sterilize half the planet. Now about simpler, but no less curious oddities, hypervelocity stars. These are stars that are hurtling through the galaxy at speeds of more than 1,000 kilometers per second, fast enough to leave the Milky Way forever. Where does such speed come from? This is usually the result of a close encounter with the supermassive black hole at the center of the galaxy. The star flies too close, its partner from the binary system is captured by the black hole, and the first star is thrown out as if from a catapult, and she flies away, leaving her home forever. Several dozen such stars have already been found. Some have almost left the galaxy and are flying away into intergalactic space. Imagine, you are a star, you have been spinning in a quiet galaxy for billions of years, and then one day you are thrown into the cosmic void. There is not a single neighbor around, nothing, loneliness for billions of years. And then there are the stars of Tornazitkov. It is a hybrid of a neutron star and a red giant. Imagine, a neutron star is inside an ordinary star, in its core. How did it happen? Most likely, two stars in a binary system, one of which became a neutron star, and then they got so close that the neutron star was swallowed up by the shell of the other. Such objects were predicted theoretically, but the first candidate was found only in 2014. they are very difficult to distinguish from ordinary red giants. Now about the planets. We are used to the planets revolving around the stars, but there are orphan planets, planets that are not tied to any star and fly around the galaxy on their own. They were thrown out of their native systems by gravitational interactions, and now they roam in the dark. According to some estimates, there may be more such planets than stars, billions and billions of dark, cold worlds where there are never dawns. And there are planets that are very strange. HD 189733b is a gas giant that rains molten glass, horizontally, with a wind speed of 7,000 kilometers per hour. Imagine, you are standing on this planet, if you could, and you are hit by a horizontal shower of glass shards that travel faster than a bullet. Or the planet 55 Cancri, which is possibly covered in an ocean of lava. The temperature on the surface is 2,400 degrees Celsius, the atmosphere is made up of evaporated rocks, one side of the planet is always facing the star, tidal capture, so there is an eternal day with hellish heat, and on the far side there is eternal night, but it is also not cold. And PSRB 1257 plus 12 are planets that orbit a pulsar, around a dead star. How they ended up there is a mystery. They may have formed from the remnants of a star after a supernova explosion, or they were captured later, but imagine the conditions on such a planet. Instead of the Sun, there is a tiny spinning neutron star that regularly bombards you with powerful radiation. There is definitely no life there. By the way, about life, Fermi Paradox, if the universe is so huge, if there are billions of stars and trillions of planets in our galaxy alone, where is everyone? Why don't we see traces of other civilizations? No signals, no megastructures, nothing at all, silence. There are many explanations. Maybe intelligent life is incredibly rare, maybe civilizations destroy themselves before they become interstellar, maybe they exist, but they are hiding, or their technology is so advanced that we simply don't recognize it, or we are the first, or the universe is too big, and we just didn't meet. Each version sounds either depressing or creepy. And then there's the Great Filter hypothesis. The idea is that somewhere on the path from the simplest life to an intergalactic civilization, there is a barrier that almost no one crosses. The question is, have we already passed this filter? For example, the origin of life is incredibly rare, or is it still ahead? If it is ahead, this is bad news. Let's get back to anomalies. The CMB is the afterglow of the Big Bang. It fills the entire universe and is very uniform, but there are oddities. A cold spot is an area on the map of the CMB that is colder than the surrounding space. It's too cold, according to statistics. Such a stain should not have appeared. One of the versions is a trace of the collision of our universe with the other, multiverses. Parallel realities, that's it. It sounds like science fiction, but physicists are seriously discussing this version. Another oddity of the CMB radiation is the axis of evil. No, it's not a faction in Star Wars. This is a peculiarity in the distribution of the temperature of the CMB radiation. Some harmonics are lined up along a certain axis. This shouldn't have happened if the universe is truly homogeneous and isotropic, as we thought. It is not clear why this is so. Some scientists believe that this is just a statistical accident. Others think that we are missing something important in our understanding of cosmology. Another mystery is the lithium problem. After the Big Bang, hydrogen, helium and some lithium were formed in the universe. We can calculate how many, and the calculations agree perfectly for hydrogen and helium, but there is 3 times less lithium in old stars than it should be. Where did he go? Maybe the stars somehow destroyed it. Or are our models of the early universe incomplete? Nobody knows. Now about cosmic strings. These are hypothetical objects. one-dimensional defects in the structure of spacetime left over from the Big Bang. Imagine a crack in a frozen lake, only instead of ice, there is the very fabric of reality. Cosmic strings are incredibly thin, but massive. A single string from the Earth to the Sun could weigh more than the Earth. If such a string flies near you, it will warp spacetime so much that you will see a double image of stars. They have not yet been found, but they are looking for them. Or monopoles are hypothetical particles with one magnetic pole. An ordinary magnet always has two poles, north and south. Cut the magnet in half, each half will again have two poles, but theory predicts that there can be particles with only a north pole or only a south pole. A lot of them should have formed after the Big Bang, but we didn't find any. This is called the monopole problem. One of the reasons why the theory of inflation was proposed, the ultra-fast expansion of the early universe. Inflation has smeared monopoles so that their density has become negligible, and it is almost impossible to meet them. And now about space bubbles. The universe may not be the only one. If the inflation theory is correct, then inflation never stops completely. It continues in different regions of space, creating an infinite number of bubble universes. Each with its own laws of physics, its own constants. Somewhere the electron is heavier, somewhere the speed of light is slower. We live in one of these bubbles, and we will never know about others, because they are beyond the event horizon, unreachable. This explains why our universe is so well tuned for life. All the constants are perfectly matched. This is called the fine-tuning problem. If the force of gravity were a little greater, the universe would collapse. A little less, stars would not have formed. If the strong nuclear force were slightly weaker, protons would decay. Too many ifs. The multiverse provides the answer. There are an infinite number of universes with all possible parameters, and we are certainly in the one where life is possible, because otherwise we would not be there to ask this question. This is the anthropic principle. It sounds like cheating, but it works. By the way, about the settings, the fine structure constant is a number that describes the strength of the electromagnetic interaction. It is approximately equal to 1/137. Why this number? Nobody knows. Physicists have tried to derive it from more fundamental theories, but to no avail. Some have even suggested that this number could change over time or in different parts of the universe. So far, there is no evidence, but the search continues. Another oddity is the problem of the cosmological constant. Einstein introduced it into his equations so that the universe would remain static. Then it turned out that the universe was expanding, and he called the cosmological constant his biggest mistake. But then dark energy was discovered, and it turned out that the cosmological constant was needed, but its meaning is a problem. Quantum field theory predicts that the vacuum energy must be enormous. Observations show that it is negligible. The difference is 120 orders of magnitude. This is the biggest discrepancy between theory and experiment in the history of physics. Let's switch to gamma-ray bursts. These are the most powerful explosions in the universe since the Big Bang. In a few seconds, a gamma-ray burst can release as much energy as the sun emits in its entire lifetime. They are found about once a day somewhere in a distant galaxy. If such a burst were to occur in our galaxy and be directed at Earth, it would destroy the ozone layer in seconds. The consequences are mass extinction. Where do they come from? There are two types. Long bursts, more than 2 seconds, are associated with the collapse of massive stars and the formation of black holes. Hypernovae, short bursts, less than 2 seconds, are the result of the merger of neutron stars or a neutron star with a black hole. In 2017, for the first time, the merger of neutron stars was recorded simultaneously in gravitational waves and electromagnetic radiation. This event was called GW170817. It confirmed that neutron stars, merging, produce gamma ray bursts, and it also turned out that heavy elements are formed there: gold, platinum. All the gold in your jewelry was born in such cosmic cataclysms. Let's talk about gravitational waves in more detail. These are the ripples in spacetime predicted by Einstein 100 years ago. They were discovered only in 2015. For this, they were given the Nobel Prize. LIGO detectors have captured a signal from the merger of two black holes more than 1 billion light-years away. The amplitude of the wave on Earth was smaller than the size of a proton. To detect this, you need insane accuracy. Since then, dozens of events have already been discovered, and each is a window into a new physics. Gravitational waves travel at the speed of light, but unlike light, they pass through matter with almost no interaction. This means that we can see events that are hidden from conventional telescopes. For example, what happens inside a star during a collapse. And then there's the background noise of gravitational waves. It is searched for using pulsar timings. The idea is that gravitational waves from many merging supermassive black holes throughout the universe create a constant background hum. Recently, there have been hints that it has been discovered. If confirmed, this is a revolution. Another anomaly is the asymmetry of matter and antimatter. According to the laws of physics, after the Big Bang, an equal amount of matter and antimatter should have been formed. They would annihilate and the universe would remain empty, filled only with radiation. But here we are. This means that there was a little more substance, just a little bit, for 1 billion particles of antimatter. There were 1,000,000,001 particles of matter. This remnant is everything that exists: galaxies, stars, planets. Why did this happen? One of the mechanisms is CP violation. Physicists know that it exists, but it is not enough to explain the observed asymmetry. It means that we don't know something. Let's talk about ultra-high-energy cosmic rays. These are particles, usually protons, that fly through space with an energy close to macroscopic objects. The most energetic particle ever recorded is called the "Oh my God" particle. Oh my God particle, her energy was equivalent to the energy of throwing a baseball, only this is one proton. Where does this energy come from? No known event, neither a supernova explosion nor an active galactic nucleus, can accelerate a particle to such an extent, and if it can, then along the way the particle should lose energy, interacting with the CMB radiation, the limit of the SLC, but this particle exceeded the limit. The mystery has not yet been solved. Now about neutrinos. These are ghost particles. Every second, trillions of neutrinos from the sun pass through you. You don't feel them. They almost do not interact with matter. To stop neutrinos, you need a light-year thick layer of lead, but sometimes, very rarely, a neutrino collides with an atom, and we can detect it. Neutrino observatories are built deep underground or underwater. Ice cube in Antarctica is a cubic kilometer of ice studded with detectors. Neutrinos from space are caught there. In 2018, for the first time, it was possible to associate a cosmic neutrino with a specific source. The Blazer TXS 0506 plus 056. This opened a new era, neutrino astronomy. Neutrinos also have mass. This became clear relatively recently, and for this they also gave the Nobel Prize. According to the standard model of particle physics, neutrinos should be massless, but they oscillate. They turn into each other in flight. This is only possible if they have mass. This means that the standard model is incomplete. Physicists are excited because it's a hint of new physics. By the way, about the standard model, it describes all known elementary particles and the interactions between them, except gravity. Gravity is described by Einstein's general theory of relativity, and these two theories are incompatible. They both work great in their fields, but when you try to combine them, it turns out to be nonsense. This is one of the main unsolved problems of physics. There are attempts, string theory, for example. The idea is that elementary particles are not dots, but tiny vibrating strings. Different vibrations mean different particles. It sounds nice, but the problem is that the theory requires the existence of 10 or 11 dimensions. Where are the other measurements? Collapsed on a scale that we cannot observe. It is not yet possible to verify this experimentally. Critics say that this is not physics, but mathematical philosophy. Proponents say it's the best we have. Another attempt is loop quantum gravity. There, space-time is discrete, consisting of tiny loops, also beautiful, also unprovable yet. Let's go back to space. The Boomerang Nebula is the coldest place in the universe, except for laboratories on Earth. The temperature there is -272 degrees Celsius, only 1 degree above absolute zero. It is a dying star that ejects gas at a speed of 600,000 kilometers per hour. The gas expands so quickly that it cools to these extreme temperatures, colder than the background radiation of the universe. And the hottest place is the center of a supernova explosion or a merger of neutron stars. There, the temperature reaches trillions of degrees. At this temperature, matter turns into quark-gluon plasma, a state that existed in the universe microseconds after the Big Bang. Let's talk about zombie stars. When a white dwarf in a binary system sucks matter from a companion, it can reach the Chandrasekhar limit, the critical mass at which a thermonuclear explosion begins. It is a type Ia supernova. The star is completely destroyed, or not. There are cases when a star survives such a supernova. These are zombie stars. They exploded, but not enough to destroy themselves completely. Now they continue to exist, crippled, but alive. Astronomers have found several candidates. How they survived is unclear. Another strange thing is stars with a shortage of metals. In astronomy, all elements heavier than helium are called metals. The first stars in the universe consisted only of hydrogen and helium. They're called population 3 stars, and we've never seen one. They're all dead a long time ago. One of them, SMSSJ03130.36-670839.3, contains 10 million times less iron than the Sun. This is one of the oldest objects we have seen. By studying it, astronomers are trying to understand how the first stars evolved. And there are stars with an excess of metals. Some of them contain more elements than they should be aged. They may have formed from supernova remnants, where the synthesis of elements was unusual, or swallowed the planet. Our Sun, by the way, is rich in metals. One hypothesis is that it swallowed up several planets early on. Perhaps we had a planet between Mercury and the Sun swallowed it. By the way, about the lost planets, there is a hypothesis about Planet 5. Models of the formation of the solar system show that the asteroid belt could have been a planet that Jupiter threw out of the system billions of years ago. There is no proof, but the math hints. And then there's Planet 9, not Pluto. He was demoted. This is a hypothetical planet somewhere beyond the orbit of Neptune. The orbits of several trans-Neptunian objects are lined up in a strange way, as if they are attracted by something. Calculations show that there may be a planet with a mass several times greater than the Earth. They are looking for her, but have not yet found her. If it exists, it will turn the textbooks upside down. Now about comets and asteroids. Oumuamua is the first known interstellar object to visit the solar system. It was discovered in 2017. It flew past and astronomers had several weeks to study it. The uniform is elongated, like a cigar, or damn it, it depends on the interpretation of the data. It moves strangely, accelerating as it flew away from the Sun, for no apparent reason. Comets are accelerated by the evaporation of ice. but Oumuamua showed no signs of cometary activity. One of the versions is a hydrogen iceberg, the other is a piece of the planet destroyed by tidal forces, and Avi Loeb, a respected astronomer from Harvard, suggested that it was an alien probe or even a solar sail. The scientific community was skeptical, but the discussion continues. The second interstellar object, Comet Borisov, behaved like a normal comet, so Oumuamua remains a mystery. Let's talk about galaxies. Most galaxies move away from us due to the expansion of the universe. But some are getting closer. Andromeda, the nearest large galaxy, is hurtling towards us at a speed of 110 kilometers per second. In 4 to 5 billion years, we will collide. It sounds scary, but the stars are so far apart that direct collisions are unlikely. Galaxies will simply pass through each other and then merge into one large galaxy. Some call it Mlechamd. The Sun is likely to survive, but it will end up in a different orbit. There are cannibalistic galaxies. Big galaxies devour small ones. The Milky Way is now devouring the Sagittarius dwarf galaxy. This is a slow process, taking billions of years. Traces of past absorption are visible in the form of stellar streams surrounding our galaxy. And then there are galaxies without dark matter. This is strange because dark matter was thought to be an integral part of any galaxy, but they found a few dwarf galaxies where there seems to be no dark matter or very little. One of them is NGC 1052, DF2. How did it form without dark matter? Maybe it was ejected by tidal forces from a larger galaxy, or our measurement methods do not work on such scales, a mystery. There are jellyfish galaxies. These are galaxies that move through the intergalactic medium so fast that the gas from them is pulled out, forming tails similar to the tentacles of a jellyfish. Stars form right in these tails. It looks beautiful in the pictures. And there are ring galaxies. Imagine a galaxy in the shape of a ring with a void in the center. How does this happen? This is usually the result of a collision. One galaxy passes through the center of another, and the shock wave triggers the formation of stars in the form of a ring. Hoag's object is one of the most famous examples, a perfectly circular ring of young blue stars around the central core of old yellow stars, just perfect symmetry. Now about superclusters. Galaxies gather in groups and clusters. Clusters gather into superclusters. Our Laniakea supercluster includes about 100,000 galaxies and stretches for 500 million light-years. We are on the outskirts. This is our cosmic address. But the universe is even more structured. There are walls, giant clusters of galaxies that form the filaments of the cosmic web. The Great Wall of Hercules' Corona Borealis is one of the largest known structures in the universe. Its length is 10 billion light-years. This is a quarter of the observable universe. How did such giant structures manage to form in 13.8 billion years? This is a challenge for structuring models. The cosmos is full of paradoxes. Here, for example, is the information paradox of a black hole. Quantum mechanics says that information cannot be destroyed, but if something falls into a black hole, information about it is lost forever, because nothing can get out. Stephen Hawking showed that black holes evaporate by emitting Hawking radiation. In trillions of years, the black hole will completely evaporate. What happens to the information? Is it destroyed or encoded in radiation? Hawking first thought that information was being lost, then he changed his mind. Now most physicists believe that information is preserved, but it is not clear how exactly. One idea: the information is recorded on the event horizon of the black hole, like a hologram. This led to the holographic principle. All information about a three-dimensional volume can be encoded on a two-dimensional surface. It sounds crazy, but it is supported by different approaches to quantum gravity. And the last thing, heat death of the universe. If dark energy continues to accelerate the expansion, the universe will get bigger and colder, in trillions of years, all the stars will be extinguished, in a googol of years, even black holes will evaporate, only a cold, empty vacuum filled with the rarest particles will remain, entropy will reach a maximum, nothing will happen, eternal darkness and cold, the end of time. Or not, maybe there are cycles, maybe the universe is shrinking and exploding again, or new universes are born from quantum fluctuations, or we don't understand what time is at all, and our predictions are meaningless. This is such a cosmos, full of oddities, mysteries, and objects that shouldn't exist but do exist. Full of phenomena that challenge our understanding, and that's great, because every anomaly is an opportunity to learn something new, each riddle is a chance to rewrite textbooks. We live in a universe that constantly surprises us, and this is better than any fantasy. Claude is AI and can make mistakes, please double-check responses.